Hello, everyone. Welcome to day 22, where we talk about correlation with a hypothesis test, of course, because it's unit 3. Okay, here's a review. We started this unit at day 19, where we talked about hypothesis testing for the very first time. We focused our attention to one sample test. On day 20, we introduced 2 sample tests. Day 21 looked at chi-squared tests. Today, day 22, is about correlation. Following this, there will be a review day and the Celebration of Knowledge 3, which is going to be over those 4 chapters. Not even all of chapter 12, because some is reserved for after the Celebration of Knowledge, day 25. Celebration of Knowledge 3 is all about hypothesis testing. And I think that all of you will just rock it, so yay for that. All right, the goals for this lesson are threefold. Understand what correlation means. See how correlation is reflected in scatter plots, and learn how to determine if the correlation is statistically significant. To do that, we're going to use a null hypothesis significance test, which some call a simple hypothesis test. Have you ever wondered, is there a correlation between 2 variables? Well, what does it mean to have a correlation? Let's take some examples. Is there a correlation between height and income? If you know somebody's height, can you guess their income? Is their income related to their height in some way? Does IQ tell you anything about a person's income? Do only smart people that make a lot of money? Or do some people with a low IQ also make a lot of money? Things like that are indicative of a correlation between them. Homework scores and exam scores, are those correlated? University endowments and acceptance rate, these are quantitative variables. Tests for independence determined if there was a statistically significant dependence between 2 categorical variables. We looked at a contingency table and we were able to determine if categorical variables were related. Today, we are looking at quantitative variables. Scatter plots are a way of visually displaying bivariate data. You recall what bivariate data is. You have a number of subjects and you look at 2 variables from each subject or sample. You can plot those variables on the 2 axes. Maybe height is the y-axis, weight is the x-axis. And so this right here represents one single NBA player. It'd be really neat if I knew which NBA player that was, but I don't recall that information. However, I know that this one person here is 76 inches tall and 180 pounds. Does weight tell you something about height? It kind of does. It kind of tells you something about height. If somebody weighs a lot, like if they weigh in this region, there's no NBA player that weighs this much and is less than 77 inches tall. Likewise, there's nobody above 82 inches that weighs less than 210 pounds. So, in a very mild sense, weight does tell you a little something about the height. That represents what we refer to as a correlation. When one variable provides information about the other, they are correlated. Contrast that with this sort of relation. This is somebody's height versus their age. Each player is represented by a single point. Does age tell you something about their height? If I told you somebody was 30 years old, does that tell you anything about their height in general? Well, they could be short and over 30 years old, and short, I mean, by NBA standards. They could be short and over 30 years old, or they could be short and under 30 years old. It doesn't give me any information. If I told you they're higher than 80 inches, does that tell me anything about their age? No, there are people higher than 80 inches in each age demographic. If they're shorter than 80 inches, can you tell me anything about their age? No, you can't. This represents no correlation. This is no correlation between height and age. No information can be gained from the other. Scatter plots and correlation. Which plot has a stronger correlation? The strength of a correlation is the amount of information one variable lends to the other. If I know their rebound, could I guess their height? Not very accurately. This cloud of points has quite a large width. If I knew their weight, could I guess their height? Perhaps a little more accurately than if I knew their rebound, because there seems to be within this band. So if I knew that they were 240 pounds, I would guess their height is somewhere in between here. I wouldn't waste time guessing that their height was down here. Now, if their rebounds, if I knew they had 8 rebounds, I don't know their height. The correlation is weaker between height and rebound. Which variable is better at guessing height? Weight. Let's get into more precise. That was more vague. This is made precise. And I hope you can appreciate the difficulty that it would be to make this definition precise. And so what you have is called a linear correlation coefficient. This is sometimes referred to as the Pearson correlation coefficient. This assigns a value to the strength of a correlation. So it takes those vague terms that we discussed earlier and makes them precise. Now when r equals 0, that's going to mean no correlation. Think about the NBA player height and age. There just wasn't really any correlation between them. Now when r equals 1, this means perfectly correlated. Height in inches and height in centimeters. So height, see, this means there is a lossless transfer of information. If I know somebody's height in centimeters, I know their height in inches. That's perfect correlation, and that's what happens when the correlation coefficient is one that gives you the end of the spectrum. Absolutely no information. And this one right here is what you might call perfect information transfer. At least that's the way I think about correlation. Now, I think about that because my background is in stochastic processes and prediction. We use stochastic models to predict the future. So I think about information gained from related variables. If this discussion were run by a social scientist, a psychologist, or a sociologist, their description of linear transformation might not take the shape of information transfer. That's a product of my background. And you'll see that strongly represented when we talk about the next lesson in day 25, which is about regression and prediction. Okay. Notation. You're making this precise. Let's look at the variables. N is the number of subjects, the number of samples. X is the data from one variable, and Y is the data from the other. X and Y are lists of numbers that are n long. We're also going to introduce Z sub X and Z sub Y, the Z-scores of X and Y. So what do? You take X, you find X bar, the sample mean, the standard deviation of X, and you use those to get your Z-scores, and this is a list of Z-scores. Now, if you do that, there's your Z, that's what Z and Y represent. Now, the Pearson correlation coefficient is defined here. R equals, and then we do this whole big formula. That's the correlation coefficient. Another way of expressing this is you take the sum of X minus X bar and Y minus Y bar, and you divide by N minus 1 times the standard deviation of X and the standard deviation of Y. This is often called the covariance of X and Y. We will not be computing this very much. We're going to let Excel do that, but it's important to know what it does. If you look at this, if you interchange X and Y Would it make any difference? No. If all of these became y's and all of these became x's, and same on the top, in fact, you would get exactly the same number. So it doesn't matter if you put in one data set first and the second one second. You get exactly the same thing. Suppose I scaled x, so I multiplied all of my x values by some constant c. If I multiplied them all by c, I would get this, and notice that this c can factor out, come up front, and c squared would come out of these terms, and that could come out of the radical. So I can take a c out of the top and the bottom, and those c's cancel, and I get my original r. So if I multiply one of my data sets by some constant, the correlation remains unchanged. That is such a clever way of formulating it. Okay, let's take some examples here. So the correlation is always a number between -1 and 1. Multiplying each value of either data set by the same number doesn't change r. That's what we just discussed. Interchanging x and r will not change r. We talked about that as well. This only tells the strength of the linear relationship. Now, I must say, if you had data and it looked like this, okay, clearly there is some correlation going on there, but it isn't linear correlation. It looks more like a quadratic correlation. This right here is not going to have a very good r value because r is not looking for quadratic correlation. It is only looking for a linear relation, all right? And r is very sensitive to outliers. Here's my data set, my points here, and I get r of -0.915. If I added another data point right there, it would drastically change my r value. It would be less negative, maybe -0.1 or 0.2. It's very sensitive to outliers. Let's look at these plots here. So here's a plot, and you might guess this is a very strong correlation. If I knew my x value, it tells me a lot about my y value. My y value is in this little band here, which really narrows down my guesses for what this y value is. So that's a very strong correlation. This one here is not super weak. I mean, it's there. It doesn't give you a lot of information. And so this is r equals 0.667. This one here has a fairly good correlation. If my x value is here, well, then that suggests that my y value is somewhere in this band. That narrows it down a bit. Not as good as with the, but pretty good. Notice this one here, this is a negative correlation. As x increases, what happens to my y values? They decrease. As x increases, y values decrease. That's a negative correlation. Those are inversely correlated. If my x value increases, so does my y. All right, and then this one here we see there's very little correlation, right? There's very little information gain. If I knew my x value is way out here, what does that do? That narrows down my y value, not at all. That's a poor correlation, no correlation. And notice that the r statistic is 0. And so that's what happens if I compute this crazy r value for these points. It turns out it seems to quantify what we can observe visually. This is a strong correlation. Visually, you can see that. And the r value is very close to 1. This one here has almost no correlation, and the r value is very close to 0. And so this statistic seems to be doing exactly what we would like it to do. Okay, now here's a quiz for you. Go take a crack at it. We'll be looking at the TA. We'll be seeing if we're paying attention. Now, the hypothesis test. We have this data, and we would like to test whether there's correlation. We'd like a way of determining that there's no correlation here, and we'd like it to be statistically significant. So let's discuss that now. Is there a significant linear correlation? We need to talk about probabilities of correlations. How is this correlation distributed? All right, as before, n is the number of samples or subjects, X is the data of one variable. Y is the data from another variable. R is the linear coefficient of the sample. Rho is the true linear correlation coefficient of the population. Now, this is what the test entails. It's exactly the same 8 steps as before. We identify the claim, which is usually is it correlated or not. We negate the claim. Then we do this null hypothesis. The null hypothesis and alternative are always set up this way. Either there is no correlation or there is some correlation. This isn't always, you could have a hypothesis test that says there exists a negative or there is a positive correlation. Step 4 is the same to find your significance level. Step 5, identify the test statistic. In this case, it is a t-distribution thing. R follows a t-distribution, and this is the standard error for this test. All right, this follows the same thing. You've got R, the sample correlation. We subtract the true correlation, which we assume to be 0. Then you divide by the standard deviation of R. The standard deviation is this value right here. R standard error, this is a t-score. Okay, then you do a p-value test, always two-tailed. If this is your alternative hypothesis, then it's t-distribution. The degrees of freedom is n minus 2. Following that, you make a determination and you restate the decision in non-technical terms. Okay, is there significant linear correlation? First, the data must be random. Then the data needs to visually look linear. Also, make sure the data has no outliers because your correlation will be significantly off if there's any outliers. Now it's time for an example. The data set in Excel, in the Excel spreadsheet provided for this video, and that you can find that on the class page. So here I am looking at the class page for day 22. I'll click on this data, cars and burglaries. I'm going to share this to Excel. I'm going to save a copy. Save a copy. And I'm going to start with working at the cars data set. First, in the Excel sheet provided, gives the result of a study from the 1920s. The data, the speed of cars and the distance taken to stop. The car is driving at a particular speed, and then somebody puts the brake pedal to the floor. How long does it take to come to a complete stop? Does there appear to be a correlation between the speed and stopping time? Is it statistically significant at the 95% confidence level? Let's do our hypothesis test. Step 1. Does there appear to be a correlation between speed and stopping time? The original claim, there is a correlation between speed and stopping time. If I knew the speed, I have a little bit of information about the stopping time. Step 2, the opposite of the original claim. Speed and stopping time is uncorrelated. All right. Now, both of these can be written symbolically. I'm going to insert a row and put the symbolic notation for this statement, and that is going to be rho is not equal to 0. The opposite of that is rho equals 0. Now, the null hypothesis is certainly rho equals 0 because it's the one with equality. The alternative to this is rho does not equal 0. Step 4, alpha. 95% confidence level. 0.05. That's what that means. Okay, and now step 5. My test statistic. Why don't I go back to my table? Why don't I come back here and find this test statistic? So here it is. I'm going to go ahead and take a screenshot of it so I can paste it for my celebration of knowledge. All right, done. Copy and delete. What I need for this t equals, I'm going to need r, my correlation coefficient. I'm going to need n, and I'm going to need, well, that's about it. So let's find r. I'm going to type in correl returns the correlation coefficient between two data sets. That's what I want. So I'm going to go ahead and select Corel. Okay, array 1. Well, let's make that one the speed. It doesn't matter which one I pick. If I interchange them, it'll give me the same answer. You click enter. Now the second one, start here, right there, enter. There it is, 0.8098949. Let me see if that's really what's going on here. I'm going to select the data. I'm going to do a little plot. Go to insert. I'm going to go to chart. Where's chart? There's chart. I'm going to go to scatter. Scatter plot. Let's see. Okay. Looks like it did the job. I've got distance on one side. Distance. It looks like it's labeling my x-axis as distance, but the x-axis here is speed because it only goes from 1 to 25. It looks like there could be a linear correlation, and there aren't any outliers. So I'm going to leave that right there. There's my R. Now I need my N, and for that I'm going to do equals count. All right. Go all the way down to about there. Enter. What is it? 50. Now I'm going to set up my t statistic equals R divided by square root of 1 minus R squared, close parenthesis. I should have put a parenthesis for my numerator, parenthesis, all in the numerator, divided by parenthesis n minus 2. Close the square root, press enter. Okay, it doesn't like that. What doesn't it like? 1 minus n, oh, n. Well, what is n? There. All right, I'm satisfied. Equals 9. I think we know what we're going to do there. What are we going to do there? Well, that's probably going to reject the null. Step 6, the p-value. Same as before now. We're at home now. The p-value equals, okay, this is a t distribution, so I'm going to do equals t dot dist. Is it right-tailed, two-tailed? It's two-tailed, actually. So I'm going to put in my t value. Now my degrees of freedom, right there for now. Let me put in degrees of freedom equals n minus 2. It says it right there on the thing I pasted in. As I suspected, that p-value is quite low. All right, what do I do now? I'm just going to go step 7 here. Is p-val less than alpha? Yes, it is. I'm going to reject the null. When the p is low, the null must go. All right, now, step 8. There is sufficient evidence to support the claim that speed is correlated with being time. This sample has a correlation coefficient of 806. Okay, great. So there's the first example. The Excel spreadsheet contains real data for the distance of Neptune along with the rate of burglaries in Kansas. Does there appear to be a correlation between the data? Use a hypothesis test for significance to determine whether this correlation between Neptune and the burglaries is statistically significant. All right, let's go back to our data, the second sheet here. The first one is the distance in astronomical units that Neptune is from Earth. And then in the second column, the rate of burglaries in Kansas. So that might be like, I don't know, per 100,000 people per year. Step 1 is there is no correlation between Neptune and burglaries. What's that symbolically? That's rho equals 0. Step 2, there is a correlation, not equal 0. Null hypothesis. It's going to be this. Alternative is going to be this one. Step 4, alpha is not given, so we're going to use 0.05. Step 5, test statistic. Okay, now before I even do that, I'm going to plot this and see what it's like. I selected the data. I go to Insert. I go to Charts. I go to Scatter. This one. Okay, well, interesting. It does seem to be pretty, I don't know. It seems to make a pretty good curve here. Continuous curve. It's very interesting how well it lines up. But is it statistically significant? Or a fluke? Or what? Let's just see. So for the test statistic, I'm going to have T. But in order to get T, I need R and N. All right. R, I'm going to find using equals Corel. Whoops. There it is. I'm going to go like this for the first one and for the second one. There it is. Enter. Look at that coefficient. That's pretty strong. All right, let's see. N equals count. Count this up. I think it might have told me. Enter. 38. And that doesn't sound familiar. Okay. Equals. Here we go. R divided by. No, not R. That divided by square root parenthesis 1 minus R squared divided by N minus 2. Close square root. Enter. 21. That is very high for a T value. This is step 6, is P value. But I remembered I need to put in degrees of freedom first. And so the degrees of freedom is going to equal N minus 2. There we go. The P value is going to equal, think. Oh, it's a T distribution, T dot dis. It's a two-tailed test. So T dot dis, two-tailed, put in my X value, degrees of freedom, enter. That's incredibly small. To say there is no correlation would mean this data, Neptune and the rate of burglaries in Kansas, is absurd. But the data is not absurd. The data is a little silly, yes, but it's not bad data. I don't think that's doctored like that. Anyway, the hypothesis that there is no correlation is absurd, and we reject it. Step 7 is p-val less than alpha. Yes, so we reject the null, saying there's no correlation. Step 8 is what? There is sufficient evidence to suggest a statistic correlate between distance from Neptune and Berg rate in Kansas. I said statistical correlation. That's because there is a statistical correlation. Now, is there a causation? No, certainly not. Some people have tried to work that one out, some sort of astrological phenomenon. But I don't believe there's any causation. There is statistical correlation. It doesn't mean they're related. It just means there's correlation. Correlation does not imply causation. Always remember that. Let's do a recap. We introduced the idea of correlation as predicting one in terms of the other. Does one give information about the other? And I call that information transfer. We saw what correlation looks like on a scatter plot. And then we finished up by walking through a hypothesis test about correlation. All right, everybody, that's it. Have a wonderful day, and we'll see you in class.